fix this whole Hello? Can you hear us?
Yes.
We can hear you guys.
We can hear you.
Okay. Okay, great. Okay, so in the interest of time, I believe you have all seen the slides without any audio, so you haven't missed much. And I'll just move to the demo. Okay, so the demo is about Asian IP with IPv6 connectivity. We have, am I sharing the?
Yes.
Okay, so we have a simple SDN domain of control of 3 switches, and then we have 2 external BGP speakers who are configured to advertise IPv6 routes, and the third one on the top is our internal BGP speaker, which speaks with the rest of with the external BGP routers. And then what we have here already, you can see the BGP routes that have been received. Right. Second. Okay, so here you can see we received 2 IPv6 routes for each destination prefix. And just to make it simpler, this is what we have. One IPv6 route from the left side and another IPv6 route from the right side. And just to show that we also have the corresponding IPv6 intents, you can see there are 2 intents already in the system, which are using IPv6 specific matching intervention, and similar for the corresponding flow entries. And then we use IPv6 ping 6, and then we can see that it works. This is from one of the hosts on the left side, pinging the other, and vice versa on both sides. And just to show you that it is not something in the background hiding, I'm going to kill one of the BGP routers, the external routers, and the ping should stop. And you can see it is not working. And if we start it again, after 10 seconds, ping should start. Yeah, a few more seconds before it appears, because BGP it has to start up and exchange information, so there's a little bit delay there. And here we put it in place. And this is about Asian IP with IPv6 prefix advertisements. The second use case I mentioned in my presentation is about the IPv6 reactive forwarding, and Charles from Taiwan, who is online, he will do this part of the demo. So just give me a second to transfer the control to him. Okay, and then, okay, let's see where he is.
I just made him presenter.
You made him? Okay. Charles,
okay,
are you
hello?
there?
Yes, I'm here. And can you see my screen right now?
Yes.
Yes, so we can see you, and you can start the demo.
Okay. And okay, so hello everyone, this is Charles, and today I'm going to demo the IPv6 reactive forwarding. And as you can see, I already started the ONOS CLI over here, and there's another screen. It's for the mininet. And before I get started, I will first want to let you know that the network topology I'm going to use for the demo today is a very simple one. It's a two-level tree structure. And what I'm going to do is I want to let the nodes in the network able to ping each other. Okay, so so first I need to set up the IP address, the IPv6 address for the host. So so I'm doing so by entering some commands in the mininet, and then we can check if the IPv6 address is correctly set. Okay, now it has a global routable IPv6 address. Okay, and now I'm trying to ping H3 from H1, but this should fail because I haven't started the reactive forwarding module yet. Okay, so now I'm going to install the reactive forwarding module in the ONOS console. It should be feature install. Forwarding. Oops. Okay. Okay. Now you can see that ONOS app forwarding is already installed here. And now I will try again to ping H3 from H1. Okay. Now it works. And I will do it for the reverse side to ping H1 from H3. It also works. Okay. Now I'm going to show the flow entries here for the IPv6. Sorry, the ICMPv6 packet. Okay, you can see there's a lot of packet here, and I'm going to also show that the host location provider is also correctly tracked these two IPv6 hosts. So this is all of my demo today, and I'm going to return the screen to Pavlin. Thank you.
Thank you. Okay, so this is about the IPv6 demo. Before we move to the next one, any questions? Okay, so some of those flows are installed by default for example, for ICMPv6 to receive and send, and some of those are reactive flows. So similar what we do for IPv4, we do for IPv6. So those, I think, or maybe he has done some other experiments with others. But basically, you will get more than one flow entry by default. Okay. Any other questions?
One question. So the open flow also is enhanced to run on like the connection between the devices and the controller.
Can you, okay, first can you repeat for me the question?
Communication between the devices and the controller is IPv6 or IPv4?
Oh, okay, so the question was whether the connection between the devices and the ONOS controller is IPv4 and IPv6. And the answer is it is IPv4. It is outside of what we have done. There's nothing to prevent it to use IPv6. It is just orthogonal to this.
Just work already.
Yes, it should work. Okay. Any other questions? Okay, so we'll move to the next one, which is Internet to deployment. And just give me a second, and can I get the presenter back.
You want to send it back to Luca, right? You need it?
Yes, I want to open Lucas' slides.
Either I move there or but I need just
Okay, so
So hi everyone, this is Luca and I'm going to present the work that has been done during this release with the help of Pavlin, the guys of Internet 2, and me for the Internet 2 deployment. So I left you a couple of weeks ago with, I guess, a quite good news that we succeeded to deploy in the Internet 2 test lab successfully the ONOS and SDN IP. So the challenge at that point was this. So we developed lots of custom hacky patches just related to deal with the flow space firewall, right? And in the meantime, we discovered anyway such number of bugs on the ONOS side, which was anyway good because we corrected them. Okay, so the challenge here was to pour all these fixes, the hacky fixes just related to the misbehavior of the flow space firewall, to the flow space firewall. And this is what we did in the last sprint. So the good news is that currently we can work with the flow space firewall with a clean version of ONOS 1.0.0 without any additional patch, okay? Other important thing that we did was to create a complete documentation for Internet 2 in order for them to be autonomous as much as possible and install and deploy ONOS on the real testbed, okay? So what's next? So first of all, well, for sure, we will support on our side the Internet 2 guys to deploy ONOS in the final testbed. In the meantime, we will start immediately to do the testing process that we did for ONOS 1.0 with ONOS 1.1.0 in their test lab. On the other side, the Internet 2 guys will use the documents provided. We'll test for about 10 days ONOS in their test lab on their own. They will reinstall it from scratch. And then they will start the deployment, engaging the university and going through all the technical process. That's where we are. So the new deadline, I guess you saw it in the first slides that Bill presented before. As you may understand, there are lots of not just technical, but also logical issues behind a deployment like this, like testing and all other stuff. So we moved the deadline to March 16, okay? So hopefully for that date, we'll have something really working on the final network of Internet 2. Any question? No? Okay, thank you.
Okay, are you going to drive your own?
Projector, can you share my desktop?
Okay, next up is Simon.
Yeah. Hi there. So this is Simon, and just an update.
Sharing your screen? I don't
Oh, I'm sorry. I have to actually let you see my screen. Okay. Yeah. Okay, good. Hi, this is just going to talk about what we did for this sprint just gone, so that's the last 2 weeks. And then at the end, I'm going to give you a quick overview of what we've achieved with the UI for this release as opposed to where it stood in Avocet, and then a very quick demonstration.
You have to also do, not this, a better one.
Okay. Can somebody project?
Oh, okay.
The other one.
You can go on.
Okay. So basically, what we needed to do for this sprint was complete the migration of the topology view from the old style of code to using AngularJS. And then as a couple of bonus items, we worked on creating a framework for a programmable toolbar with different button models. And also some work was done on the server side to write Java classes to support runtime dynamic extension of the UI. So that was what we were aiming for, and I'm pleased to say that we managed to hit all of it. So with the topology view, we completed the migration to AngularJS. Now, instead of one huge 3,000 plus lines of code JavaScript file running the topology view, we've got it broken out into a number of submodules where the largest is still a little bit hefty at 865 lines of code, but the typical size for each of these modules is 200 to 300 lines. And obviously that will really help as development goes forward with people being able to work on different parts of the UI without stepping on each other's toes and creating merge conflicts. We have now fully implemented the light and dark themes, so you can toggle if you like a light background or dark background, your choice. We re-implemented the different views that we had not done at the end of last sprint, and also reintroduced the radio buttons for filtering out just the packet layer or the optical layer of the network topology. And then as an addition, due to popular demand, we now can hover over links and see the port numbers displayed on those links. As I mentioned, we've also created the beginnings of a toolbar service. So a view that wants to create a toolbar and attach behaviors to the buttons can do so. We also added a small feature to the mock server, which basically does a fast run through an initial set of events to speed up the development cycle for testing server-client communications. And as mentioned, we also have the UI extension service on the Java side. We've actually got, so the way the UI extension service works is basically you can, on the server side, you can register a UI extension implementation, and that basically tells the server where it can find the JavaScript, where it can find the CSS style rules, and so on. And basically those streams get injected at runtime when somebody requests the web page and asks for example, the index.html. That file is actually generated on the fly on the server and injects all the appropriate resources. And so we've actually got that mechanism working. So this final slide here is basically a look back to December to now, just to see what we've done with the UI. And you know, it's nice to see a large amount of work done here. Particularly important is the fact that we're now using AngularJS as our framework because it provides the modularity, extensibility, and testability. And we've got, I think, at last count, about 290 unit tests. So we're actually testing the client-side code for expected behaviors and so on. So yeah, another thing that you've seen in previous demos is the device list view, and I'll just remind you of that as we go. So probably enough talking and show something useful, right? So,
Question.
Oh, there was a question?
Yes. How can, okay, I can read it.
how was the breakdown to module affected the initial page load times? It's still pretty quick, so I don't think it's really made a big impact. And you can see that as I do this, hopefully. So I'm just going to launch the UI. Bam, there you go. This is actually the, so I should probably explain, we've got the, this is, what you're seeing at the moment is the Avocet release of the UI. We have both the Avocet and the Blackbird UIs co-located. So by default, you will get the Avocet release UI. And if you look up at the URL here, you'll see that the Avocet UI is based off a legacy subdirectory. So to get the Blackbird release directory, you need to, for now, just remove the legacy directory, and you can see almost no difference, right? But this is actually running the AngularJS-based code, and as promised, we now have link highlighting, and if you can look closely, you can see the port numbers on each end of the link. This feature can be switched off. If you remember, you can press the /bar or the question mark key to see the quick help, which gives you a summary of all the key bindings for this particular view, one of which is P, toggle port highlighting. So if, yeah, we have an issue with my emulation running in the background, I think. So if you want to disable this highlighting, you can just do that with the P key for now. So I did want to show you a couple more things. Just as a reminder, we have the device view. So this is actually talking to the server and asking for a list of devices and then creating a table. And we have sortable columns so that we have that mechanism available. Although this particular data isn't particularly interesting for sorting on, since it's all the same, but the mechanism and the behavior is here. We have a temporary navigation by clicking on the bird here. We haven't yet decided how we're going to visualize this properly, but basically you will be able to switch between views. So in this case, we're just going to show you a sample view, but if you look down in the bottom corner, you can see now we have a programmable toolbar. And so this one has just regular buttons, toggle buttons, which maintain their state, toggled or not toggled, radio button set, behavior, and each of these button types are available. Here's the source code that does that. We basically use a reference to the toolbar service, create a toolbar with a unique ID, and then say add button, add toggle, add separator, etc. So it's very easy to program from a Vue developer's point of view, and then they just provide the callback functions. When this button is pressed, call this function. So it's, I think, a pretty simple model for being able to do that. So yeah, that's it. Are there any questions?
Yes, there are follow-up questions from David. Okay, so,
Hi, David.
Okay, his question was about you can see directly. It's about
okay, the first question I had was really about the performance, right? You're doing all this on a local machine, so the GUI's naturally fast.
Right.
Just in terms of a real-world use case, likely the client could be on the far end of a WAN, could be on a much slower link.
Sure.
Than you're saying. So just in terms of testing and understanding page load times, it's probably important to look at that. It still may load fast. I like the UI design, to be fair. You know, it's light on graphics in some sense. It's sparse, which I tend to like,
Right.
but it's something to think about. The other question I had is when you showed a table, you showed 25 devices. Great. What happens when there's 1,000, a million? taking things
Yeah.
like paging into account, being able to query, kind of Google query. I want all the devices with this characteristic. Boom, show me that
Yeah.
list so that I can drill down.
So I guess in response to your question, we're kind of taking it step by step. We have Jira tickets on our backlog to address some of these things. We just haven't given them any CPU time right now. So,
yep,
but they're
enough.
definitely in our mind.
All right, thank you.
Sure.
And since you can flip between the light and dark, so how does the dark one look like? Is
Sure.
it just very simple switch, or is it?
Yep, it's a single switch like
No, that is the easy part. But how does it look?
well.
Okay.
So. Okay. All right. Any other questions or comments?
We should probably move along.
Yeah.
We're getting right behind.
All right. Thank you, projector.
All right, we have one more demo before we get into performance, and that's Hong Tao.
Are you lost? Okay. Can you?
Here.
You must stop it. You can start.
Sir?
Yeah.
Hello, everybody. I'm Hong Tao. I will present our work on the IP run use case. Actually, our work is not limited to the IP run use case. We just want to create a more general service data in the ONOS, and so that the upload the application and the service can push the service data to the device directly. So that's why we set the service data installation and the extension in the ONOS. It's not limited to IP use case. But we will use the IP run real network scenario to test our to do some testing and to build our the code based on the IP run use case. Okay, so we know that from the real network, we have various the network application and service. This service needs to set up some like L3 VPN, this kind of network service. And one simple way is to create a channel in ONOS to push this data to the device directly. And this service data can be any kind of the configuration or commands, whatever, this kind of data. And this data, actually, the ONOS doesn't care this data. And the application and the device understand, both guys understand such data. So application sends the data to device can translate the data and install it in the table. And also this supports normally for the service application service right now. This supports the multiple table. So that means the service can install in the multiple table. So this is naturally an extension to the ONOS Fluoro subsystem. So our purpose is to extend the ONOS Fluoro API and also include the core. In the API part, we try to build a unified Fluoro API interface. So this interface will include the current ONOS Fluoro API and also plus our extension, the extension API. And in the core, we also build a subsystem. So eventually we will integrate with ground ONOS fluoro subsystem, and we also tested. And I will show you some of the demo results later. Also, okay, the ground implementation is that we add a fluoro API extension package to ground ONOS fluoro API, and also add some control modules to the subsystem. And the main work we did right now is we just tried to give a service data abstraction, because this service data is not visible to ONOS, and there is originally the service data is pushed to the device. It's just in the string of the correct string form. So so right now we want to give abstraction, and we have to create a framework for such abstraction, so we can add the some common feature in the service data like length, type, and some common operation, like add a new update or this kind of thing. And another work we did is we are trying to build a unified fluoro API interface, and also we have built a framework use the current API and combined with our extension API. Use this unified API, so the third-party application just call this use this unified API. So don't need to to call a different API. And also we try to integrate our subsystem with ONOS fluoro subsystem. Currently, we just use a routing mechanism in our subsystem. That routing mechanism can handle the data from application to distribute to the different ONOS instance and push it to the device. So this routing module can figure out the master shape for each the service data installed to the device. And this is our current work. We also need to do some integration in our work. Okay, so we also test our ground implementation. The test setup is we use 3 virtual machines. One is for Mininet to generate a network, and 2 ONOS instances. One controls 7 switch, and another one controls 1 switch. But among these switch, we use 6 OpenFlow switch, the virtual machine generate the Mininet generate, and we also use to simulate the one-way switch. This simulated switch much like the real switch. It's maybe not OpenFlow. It's maybe OpenFlow, whatever. So, so this is as a setup. Here we have some test results. Firstly, we let the application. We also, besides this extension, we also build the application and also the southbound provider. And we built the Huawei agent in the provider. So the third party, they can just build their own application and their own driver. Just use our extension code. So firstly, the application can get the topology and use the topology information, can push the service data to the ONOS core, use the extension API, and after the API gets the service data, because the device ID is coming with the service data, so the extended subsystem can figure out the master for each the service data. Which guy is responsible for pushing this data to the device. So firstly, we tested the system initialization. We started and everything is fine. We can build the master chip, and then we tried to install the flow and use the extension the interface. The flow rule is here. We give the example is so the flow rule is installed in ONOS instance 1, and after installed, we check the result from ONOS instance 2. So ONOS instance 2 can show the flow rule installed on the device, and then we also test the intent, P2P intent. We built point-to-point intent. We can verify currently the ONOS subsystem flow rule subsystem working correctly, and also our extension subsystem also working correctly, and our subsystem will not impact anything on the ground ONOS performance. And we also did the pin over the path. And actually, this test is done fully. I just give a couple of pictures to Emma. Okay. So for this work, I would like to thank Thomas, Ali, and Brad. We discussed a lot of things, and they gave us much great suggestions. And we will continue our work on this part. Thank you, guys. Any questions?
What's the relationship between the flow rule and the intent API? Those are correlated between them, or separated? And your flow rule API, come intent API, or just separate?
No, we don't use the intent API. We use the flow rule API. Currently, it's separate. Yeah, we will merge it and build a unified. In my slides, we will eventually build a unified interface, and we also we already built a framework for the unified interface, and later we will add more contents in the service data abstraction. We will add the length, type, this kind of information. Actually, because the service data is very complicated, we can imagine. In a real network, we have the different kind of service requirements, different service data we need to push into the device. So we need to figure out some common features. We need to do some abstraction.
In that sense, I try to understand that the intent is a more general, more high-level API, and the your stuff is a more detailed of the abstraction. It's not high-level abstraction. If I don't think it's going to be merged into the single framework, rather might be a different layer. It's high-level as an intent, and then your more detail of the abstraction layer below.
Yeah, our case.
I don't.
Yeah.
Our case.
So I probably can answer this question. So the flow, the intent API is just a set of the path from A to B, right? So what content flow in this path is installed by this API. So the flow rule API, so it's a separate thing. So that's what we call the service installation API. It's not the intent. Intent is the build of the autonomous path. So some things we need a flow into this path. We need to build up the flow and install through this.
Yeah. Therefore, my question is that, yeah, I know. Therefore, my question is that finally, what kind of implementation should look like? Is everything can be merged into the intent layer, or you have a two layer like intent layer and maybe intent sub layer, having a more detailed abstraction handling.
I think we propose producer and consumer models. So the one is the producer. So the producer is provisional network. It's through the applications, right? So the consumer is who's going to use this tunnels. It's the consumer. Producer and consumer can be separate or the merged. So it pretty much depends on how you implement that.
Patrick, is it okay if we move it to the end of the? Oh, thank you.
Okay, so
right.
A grand topic.
All right, so let's move forward with the ONOS performances. As usual, we'll go bottom up. So Ali will start with things related to the flow subsystem, and then we'll move up to the core and the intent API, then to arrive to the final test result. Okay? So I leave it to Ali.
So, not much has been done more than what was done in the previous sprint. We've provided null providers to give you null, to give you zero resistance southbound for testing. They're available for all the southbound subsystems, and they're also configurable to allow you to provision a network that you'd like to have. So the various topology subsystems have been kind of rejiggered a little bit so that they avoid doing things that are unnecessary ahead of time that weren't used. So we avoided pre-computing paths unnecessarily, and we've added a driver subsystem so that you can inject abstract device behaviors into the system. Can you move to the next slide? Sure. Yeah, that's fine. Yeah, that's fine. No, okay. Yeah. I'll leave the intent part for Brian to talk about. The floral subsystem has, as you already know, probably has been redesigned. Well, redesigned. The internals have been redesigned. The API has mostly stayed the same. It removes a lot of complexity and is much more deterministic. We've added an application subsystem so that you can inject applications at runtime and they'll be distributed across instances. Next slide. I don't know if I'm going to go through this whole diagram, but that's basically the working model of the flow subsystem, how an app submits work, how it's split up, how it's parallelized, distributed, and then passed to the correct node for installation, and then the update is done out of bound to update the different neighbors. Next slide. So probably the thing you haven't seen is kind of like some performance numbers for the flow subsystem. So the nice thing is to help the test team, I gave them a small test script that allows them to generate numbers easily, which they did. And on the right side, you can see the chart. So if most of these results are kind of to be expected. So if you have no sideways communication, you get roughly a pretty good scale up in terms of performance. So we can hit close to 3 million flows per second, which is pretty cool. And then as we scale the number of neighbors, of course the performance in terms of installation goes down a little. But in the worst case we've tried, where we have six neighbors and therefore 7 instances, we still hit about 1.5 million flows per second, which in my opinion is more than enough for now. Until the day where people give us switches that can install 1.5 million switches flows per second, we're happy with these numbers. Well, at least I'm happy with these numbers. S is servers, I presume.
Number of servers you installed or running the testing.
So
number of servers.
So okay, let me maybe say this in more detail. So the test scenario is kind of simple. You start off, you have a number of ONOS instances, right? Initially, you say they talk to 0 neighbors. So that means that each ONOS instance installs flows for the devices that it's local to, right? So the local devices that it's connected to, and then you increase that number, right? So you slowly say, okay, now you have 7 instances. Say they each talk to one neighbor, and you have two. You increase that number to 2 neighbors, and so you're slowly scaling up the sideways communication, where you distribute flows amongst instances, and that's it has to happen, but it's overhead compared to the case where you just install locally to your local switches. That's why you see a performance step down, because you have to communicate sideways and then push it down and then come back up, right?
When you have 6 neighbors, it needs to go to everyone.
Yeah. So everybody's installing flows for everybody.
What does it make? I guess I don't understand how one ONOS instance could have 6 neighbor ONOS. If there's only one ONOS instance total, how could it be?
No, there are 7 ONOS instances total. In the yellow case, right, where S equals 7, you have 7 instances in total. You have 6 neighbors.
In S equals 1, that means 1 ONOS instance,
right?
And so how could it? But it still has an entry in the 6 neighbor column.
Do you have multiple instances on the same server?
You have to ask Subin. I don't know.
Why don't we send
Yeah.
to the end?
Yeah.
So there's more. This was just like a.
Well, I guess the chart just doesn't make
This chart was an amuse bouche to what comes later.
Can we go through the
Yeah.
the whole development work first?
So the answer is nobody understands it.
Well, no. So
No, the answer is we'll see it in 10
The
minutes.
question is that after the
5 minutes.
discussion,
yeah.
we can give you more scenario how.
So you guys don't understand it either.
I was going to say that's not.
We're going to go through the same chart in 5 minutes. That's why
Okay.
it was his work. So
Is there a question from the audience? Actually, David, you can ask a question on the phone.
Okay, I'll try to ask it this way. I was just curious. I was thinking back to how kind of some of the Hadoop stuff deals with it, right? When I have 7 neighbors, does this mean I replicate to all my neighbors before I consider the flow transaction complete, or is there a way to say, look, I've replicated the 7 or 3 of the 7 neighbors, I can consider that complete because now eventually the others will get it. I don't necessarily have to wait till it be replicated everywhere.
So in this case, the way we consider an operation as being complete is when we get an acknowledgement from the remote neighbor that the installation has been successful.
So if I have 7 neighbors, I have to wait for acknowledgement from all 7 neighbors before it's complete.
Yes, that's how we measured our performance. Now, you as an application don't need to care because the API is asynchronous. So you submit your work and you go off and do nicer things. But from our performance measurement, the way we got the numbers, we submit work and then we see when the work is complete. But from an application's perspective, you don't need to care unless you really want to care.
But if I'm an application and I want to get notified when the work's complete, I will get notification when all the neighbors are successful.
Right, and that you'll get a callback. You'll get a callback telling you, and the callback is kind of nice. It's a piece of code that you can inject. So you can inject some code in there, and it will implement it for you. So you can change your installations however you see fit.
No, and I get that. I was just wondering if ONOS can learn from some of the big data, the Hadoop Cassandras, who basically said, look, if 3 of the people get it, I know eventually all get it, and now I can give that callback sooner. And you have to deal with eventual consistency.
I think you're conflating 2 things. You're thinking that we're distributing the data for HA. We're not. Here in this case, we're distributing data for installation to the switches. Right. So we have to talk to everybody to get it installed on all the switches.
Okay.
It's not about distributing data for HA.
Okay.
Maybe I can restate this, David. In this case, number of neighbors here means the number of switches in this transaction, not including myself. So when you have 6 neighbors, you've got a 7-node cluster. That means that this transaction, this flow transaction, has work for every single node in the cluster because we divide the devices where each device has one master. We can't necessarily push down work given the current model, we can't push down work from a single node to any switch. We have to route it to its master, and then the master pushes it down.
Yeah, I get that. The bit I was missing was in this for performance test, there were nodes on each member of the cluster that had to get this thing down as opposed to, as it was hinted at, data replication. It was actually the data had to get to that node in the cluster to push down to a network element. That was the bit I was missing.
Yeah,
So,
sorry about that.
Oh, no. I'm sure it was all me.
No, I don't think
Questions about the API?
Yeah.
So the thing is, this is asynchronous API.
Yeah.
But if an application wants synchronous behavior, let's say it wants to be very simple, it should be trivial to put a shim layer on top of what you have.
Yeah. So
and then you can provide this semantic.
So the way it's asynchronous is when you build up your batch of work to install, you have the option to add a callback, and that callback will be will trigger back into into the application's code. Right? So once you install, you'll get a method, you get a callback on success or on error, and you can do whatever you want there. So you can add your shim layer there if you want, or not.
Or you can add it.
Or I can add it, but I probably don't want to.
No, this is
unless there's a compelling reason to do that. Huh?
Well, anyway, we can take it offline.
Yeah, we can.
If you're answering all these questions, why aren't we explaining that on the Bob's question? I think it is bothering me as well. Then a single instance, how can you have so many?
That's, I mean, it goes thinking of data now, even thinking of data now.
Go for it.
And you want to go to the wiki page?
Sure. Does it need to go to?
It's just a simple semantic.
Simple
explanation. No, I have the configuration.
How can one know?
Let's look at my configuration setup first, because this diagram doesn't show you the configuration setup.
Hold on, just a second.
So click on system tests. Test results. Master branch. Performance and scale out. And then you have default, the first one, default, first. So, this describes the environment setup. The server, what it is, okay, how do we test the constant node? Basically, is that we have 35 switches, right? When you have n neighbors, those 35 switches are distributed among those n neighbors, including yourself, right? So when you install from one node, when you have 6 neighbors, that means that those flows can go to local, and some other, even distributed other flows to other neighbors. So those flows will need to go across east-west to reach.
So what you're saying, what you're saying is there's only S is the number of people who are installing.
Yes.
The parameter that's missing.
That is.
The thing that's missing, appears to be missing, is how many ONOS nodes there are.
Well, so it's the max of the neighbor or servers.
It doesn't matter how many.
It's a max of neighbors or servers. You have, let me explain. If you have 7 servers, you have 0 neighbors, you're going to have 7 node cluster. Because every node has locally installed approach. Yeah, it's not trivial. I mean, I think about it, but it's a max of servers and neighbors.
That is still not making sense.
I guess the thing that's not obvious from the chart is what the value of n is.
The value of n.
And what is n?
The number of neighbors.
N is the number of ONOS instances.
No.
Oh no.
Neighbors.
Oh, sorry. What is the total number of ONOS instances?
It's the maximum of either the number of neighbors or
server.
It's a server. It's a 7.
I mean, you could have just.
To obstruct it,
easier way of saying.
What you need to do is cover this. This will be like everything local installing. That's your scale out scenario. You have 1 server, 3 server, 5 server, and 7 server. The performance.
But with no neighbors, right?
With no neighbors, yes. You have to look at this individually.
Understood, right?
With the 6 neighbors, that means everything of everyone else, and you have this kind of scale out scenario.
Okay. Yeah, I think.
Can I try to insert something here? So perhaps the misunderstanding here is that in every experiment, every single one of these bars, there is a 7-node cluster. And the x-axis, the S number is the number of servers from which you're pushing, the number of servers that are inserting work into the system. And the the colored bar is the number of instances that are inserting work into the system of the 7 in the cluster. And then the x-axis describes how their work is distributed across the cluster.
Yeah, I just didn't see that number 7 listed prominently.
It should be. It probably should be.
6 means because we're calling it neighbor. Okay, there's nomenclature. We don't have to don't. We haven't run out.
No, but the solution to this problem is simple. Just put 7 somewhere.
But
Yeah.
6 neighbor means 6 not neighbor meaning that yourself counted 7 6 plus 1.
No, but I guess the one explanation that Brian gave that then you always have 7 servers.
Yeah, no, it's not always 7.
Okay, Brian just
That's
said
what Brian just said that, right?
He just said it.
Brian said each graph of this has 7, right? But here, and for give a particular example, this one will be a 5-server scenario. So only 5 servers in the cluster.
Brian said there's always 7 servers.
But I'm not saying that.
So, the way that you described the test scenario to me yesterday, the only way that it makes sense for the 6 neighbor scenario is if you have a cluster of 7 nodes running. You can't have 6 neighbors if you only have 4 servers.
That's correct. That's what I'm saying. Number of servers in the cluster is the max of server and neighbors. Think about it.
I think that from the flow performance point of view, so the number of the servers in the cluster is not so important. So take a look at this one. So it's the whole almost 1, 2, 3, 7. The flow one, the one is means you have the flow generators, and the dump all this the number of the flows through this instance go directly to the 35 switch. Here is what the first column means. So the second column is when the one has they have the two neighbors means you have the 3 ONOS instances involved. So the flow generators both totally generate these total numbers evenly distributed on three nodes. So there's a 3 ONOS instance to install the flows into this 35 switch. The 7 means all these 7 total number is not changed. Total number switch is not changed. But evenly distributed across all the 7 ONOS instances. So it doesn't matter.
There is a ground truth, and I would suggest that
it's my understanding.
It does matter. So there is a ground truth, which is what is the size of the ONOS cluster? And this is we told you what it was.
I told you that. Max of server and neighbors.
It's 7.
Is 1.
The server isn't the number of ONOS nodes.
Server installing, working, when the script is 1.
Right. But the number of ONOS nodes does actually matter because there is global communication in ONOS.
It matters. This is 1 node cluster, 3 node cluster, 5 node cluster, 7 node cluster.
I'm just saying that
I think the solution to this problem is really simple, right? So for every single one of those bars, put a number in it, which is the number of instances involved.
That's what I'm saying.
And this is a real number that, I mean, it is, you know when you set it up how many ONOS nodes.
Because the calculator, if you go through the presentation, then we haven't had time to really make the data more presentable and make maybe that's making people confused.
Anyway, the bottom line is really that this data is wonderful.
Don't lose track of the bottom line. Right?
Yeah, exactly. I just want to make sure that everybody.
If you only look at the yellow bars, right, which is, let's say, so those are 7 node clusters.
Yes.
All the yellow bars are 7 node clusters. Yeah. The performance starts going down if you do more neighbors.
That makes sense, right?
Yeah. You have to
What
communicate.
neighbors again?
Huh?
How many?
Neighbors are the other instances that you have to talk to.
To get a
You
flow
need to install
installed.
the flow to the neighbors.
Why should your performance
Then
go
what's the
up?
point of having 7 lateral communication?
So wait. Hold on. Everybody chill out. So
Don't we want to increase?
no. Hold on. Yes. So you do. Hold on. If you look at the leftmost group of bars, right? As you add instances and you have 0 east-west communication, your performance goes up. Now, if you take the same number of instances, right? The same number of instances, and you add east-west communication, then you're adding overhead because you have to talk sideways. So from any instance, you have to call a remote instance to tell it to install remotely. So you lose performance because you're
but that's for real, right?
You're right.
And you have to talk to other
but
instances to
it's
control
a
other
trade-off. It's a standard trade-off of a parallel execution. The more communication you have to do, the more performance you lose. Now,
right. So the comparison, Saurav, you should do that for the same number of neighbors. When you go from number of instances from 0 to 3 to 5 to 7, that performance is still increasing in this particular case. So that is what scalability is trying to show you or give you.
But I guess I don't fully understand is
you can't, right? It seems impossible to go into better. So you have a set of switches connected to one instance, right? You have a set of switches connected to one instance, right? If you have a set of switches connected to a single instance that you're installing only for those switches, then yeah, you're going to scale up, right? But
yes, but then what you're telling me is you're just showing me what is the obvious.
Well, yeah, sorry, man.
It's not that obvious, right? If you look at 7 nodes here, you explained that the sideway communication causing it to slow down performance, but why is 3 and 5 is going up, right?
I mean, there is a trade-off, right? The more, if you have your application running on every single instance, installing flows for everybody, right? Then you're going to have worse performance than if you rebalance your application to run where it needs to install flows. I mean, it's a normal thing, right? Like it's normal parallel execution. Like you split work, you increase communication, you lose performance if you over communicate. That's what this is showing. When you over communicate, you're going to lose performance. It's standard. It's ON.Lab's law. It's normal. There's no way around that.
Yeah, but networks don't work like that, right? When you start splitting work, those things are only localized. You're controlling an entire fabric, right? You can't do something and then change something, rebalance. So I only do over here. So I win by parallel execution.
But that's the whole point, right? So I mean, that's
no, right. I'm not following you. What are you saying? The pattern where the results are what you expect, right? So
yeah, it's obvious. I'm saying this is
but
obvious.
Getting the obvious with distributed system is not easy, right? That when you go from number of instances from 1 to 3 to 7, right? Will you really get performance benefit? How many distributed systems do that by default?
One thing
and it does require a lot of work to get to this point, right?
Was this done with real, like mini-net switches? No. Yeah, see, that's what I'm trying to say. If you try a real networking scenario, then this thing that you're showing me that is obvious won't be so obvious.
But hold on. So you're taking two sets of scenarios that are completely different. The point here isn't to show, oh yeah, if you stick mini-net switches or real switches under this, you'll get these numbers. That's not the point. The point of this diagram is to prove that like the ONOS core, the distributed core of ONOS, can deliver this kind of performance, right? Now, whether your data plane can support that performance is a totally different question and irrelevant.
No, I'm not asking about the data. I'm asking about a real networking scenario that has the kind of traffic that you need to support and the kind of flows that you need to put in. You actually gain anything. So you will. So what this is showing you is that like depending on how you install your flows, you will get this performance, right? And that's valuable information to have because there's a trade-off between where you place your application and how you install the flows. And that's to be expected, but that's good news because I mean that like now it's deterministic. You know how to evaluate this, and you can study the problem as opposed to before where you were blind. You were just told, okay, install something, and one time you get this performance, another time you get this performance. Now you get something that's predictable. I think that's a win. I mean, it might be trivial and obvious that we get a scale up, we have zero communication, and then we get a scale down, we get over communicated. But hey, yeah, great. That means we're still in the realm of reality. I'm happy with that. If I understand you correctly, Ali, you're saying that if your application is running locally and installing flows on the switches which are attached to that ONOS instance, then you get markedly better performance than if you're installing flows on switches that are connected. If you're running on one instance and installing on switches that are connected to others. Yeah, this remote, basically sort of the remote flow installation penalty.
Well, which is to be because you're adding an overhead.
Well, the nice thing is that you might expect an improvement though because you actually have more sort of kind of control, computation, and communication bandwidth in the distributed scenario.
Yeah, but you have to get those flows to the remote instances. there's no magic, right? It's like saying, yeah, insertion in a tree is 1. Once I found the spot in the tree where I want to insert the place, the thing. I mean, like that doesn't mean anything. Like, you have to get your data to the right place and then install it. That takes time. I mean, nothing comes for free. There's a cost to everything. It also sort of it's like saying it takes me 5 minutes to get home once I'm in San Francisco.
It seems like it should affect latency more than throughput is what I'm suggesting.
And it also points to an opportunity where, like, say, you have a controller sort of connected to multiple switches or a switch connected to multiple controllers. And if their roles are set to such a way that any one of them can actually push rules down the switch, it actually gives us, like, for example, ways to eliminate the east-west overhead.
Absolutely, and I completely agree with that. I think what this is saying is the explicit master-slave relationship that we enforce at the data plane layer. Maybe we don't need it. Maybe we can virtualize that and have everybody set as equal, and everybody can install and ONOS arbitrates that. That would be great. Then we can have a linear skeleton no matter where you install from. That'd be great.
Do we have is this the only slide we have?
No.
Just checking. Go ahead.
I'll share you to see how the tools are very good conversions. This time to complete which works, and it can be taken to the next step. And to iterate David's question, he asked a bit earlier about the HA traffic, because I guess here this is without HA.
This is with HA.
With HA. Then, well,
so the way the HA works, and we're taking a risk here, is we perform the operation, right, and as in a separate thread of the installation, we update our neighbors with the information. Well, not the name. I shouldn't use the word term neighbors. We update our backups with the information that we need to store for HA. So we're taking a risk because we have no guarantee for a small amount of time. We have no guarantee that if one instance blows up, we might lose data, right? So if we were to run the update thread synchronously with the rest of the installation, the performance numbers would go down, right? It's a question of like taste and flavors and how risky you like to lead your life.
And how many copies do you do?
So right now we do copies, if I remember correctly, 2 copies.
Now, the backup mechanism actually writes to Hazelcast in a sort of hybrid thread.
Because before we can download.
Exactly. So that is the trade-off that Ali is talking about, right?
I'm a little bit surprised you get this understood.
So it's out of bounds.
But won't it eventually fill up the pipeline, and once you fill all your buffers, won't it slow you down?
Yeah.
So I think we'll sort of get to it because we have, I think, intent performance measurements. We have seen various sort of issues, performance issues when we're bombarding Hazelcast with lots of traffic. So that is something that I think there are improvements that we made that are currently in place in the intent side of things, which we eventually want to bring down. So I'm not saying that will drastically improve performance, but at least it will not, it will prevent the system from falling over and things go beyond a certain length.
Yep.
Let's go on. Guys, if we can take it offline and.
Okay.
So, Brian, where are you?
Hi. So I think this is a picture that people have seen before, so I'm not going to spend a ton of time going through it, but I just wanted to highlight the fact that in this iteration, we've taken a big hack at the intent subsystem. We redesigned the API and the semantics of the API calls, and this was for 2 reasons. One was to simplify the programming model, and the other was to add parallelism. It turned out that a lot of the people that were using the APIs sort of had different expectations. We required them to do things like batching that was sort of difficult for them to understand the consequences of. And so we redesigned the API and the system. We've successfully re-implemented the system, and the implementation has reduced a bunch of complexity, and it's also improved readability, so it should be easier to maintain and enhance going forward. We also took a look at the intent store, and we moved away from Hazelcast and are using the gossip-based eventually consistent map. So we can go to the next slide.
Sure.
And I mean, there's 3 sort of big themes that we've learned in our diagnosis of the performance problems that we were seeing when we first started. And the first thing is, before you can do anything, you need to have stability under load. And one of the things that we realized is that the code that we ship with Avocet, and when we initially completed the rebuilding of the intent framework, if you put the system under load, it will fall apart very quickly. And once it falls apart, it's unable to do work, and it's unclear when or if it will recover. And so the good news is that today we can run the system for extended periods of time without things falling apart. So it can continue to do meaningful, useful work. You can withdraw the load, and you can reintroduce the load. And so we have a platform on which we can actually, make sense of reasonable testing. This is in part to a couple of things. First of all, one of the things that we leverage is the gossip-based store that I just mentioned. And we're also seeing in some preliminary performance numbers that we're getting, like, on a reasonably sized 5 to 7 node cluster, several thousand intents per second per node, which we think is pretty good. There might be some more headroom, but that's where some of our testing over the next few weeks is going to help us figure out where we can still make progress. The other thing that we noticed was that Hazelcast seems to have some recovery mechanisms. It has some protections around trying to create new threads when it thinks its threads are being slowed down. We are inherently competing over things like the network resource and the threads and the CPU cores. And so some of the things that we're doing under load seem to be at odds with what Hazelcast is doing to try to recover, and that can sometimes hurt us. So we need to do a better job of understanding what happens to Hazelcast and why. The second major theme is that feedback is important. We need to provide feedback or pushback to applications when the load's high. It's very easy for an application to overrun the system, and with the asynchronous APIs, it's really the calls, the overhead to applications is really low. So an application in a tight loop can easily overrun the system. And the other thing that we need to do is we need to provide feedback to background tasks so that they can do work when the system load is low. Because if a background task tries to kick in while we're trying to put up with operations in a high load environment, we found that can make things worse rather than better. And the third major theme is that pending work must be bounded. And so there were a lot of places where we were using cache thread pools, which just whenever you need a new thread, it creates a new thread. And we also, when we moved away from cache thread pools, we moved to fixed size or single thread executors. And one of the problems there is that they're backed by a queue, which can grow unbounded. And so one of the problems we were seeing in a lot of our initial testing was out of memory errors. And this looks like a leak, but actually it's just pending work that's building up and isn't getting flushed. And so we implemented a few things to help combat the problem directly. We implemented a fixed size thread pool in a lot of places. We implemented a bounded thread pool so that given a fixed number of threads, you can only put a fixed number of work items on it. And then applications that are trying to put work into the thread pool are implicitly pushed back. And that's through a caller feedback policy and Boolean that we built. The point here is that we need to protect ourselves, and we need to bound the sort of outstanding work that can be done. We've also done some stuff around when an update is in flight, i.e. pending. We want to coalesce that update with other updates that supersede it. And so that's also work that we're going to be looking into. So unfortunately, we don't have some solid numbers that we feel comfortable reporting today. But the good news is that we've identified some major themes that have allowed us to make a lot of progress in the implementation of the system. And we look forward to having some good numbers in the next few weeks. So are there any questions about the intent stuff? Otherwise, we can go on to the application framework.
So Brian, I really like this idea of limiting work in progress to prevent sort of this kind of literally distributed denial of service packages yourself. Are these, my question is, are these tunable parameters? Because it seems like they're things that either the user or the system might want to adjust based on varying conditions.
At the moment, Yeah, so at the moment these are fixed size parameters, but ideally these are parameters that could be learned by the system at runtime. But that's probably for a later date.
So if I understood that right, Brian, some of the work is bounded, so I can say kind of finish this task within 5 minutes, or don't finish it, or error out, or something.
So we don't have the APIs that would allow you to do that. The way that the APIs work now is there's just one asynchronous API. You attempt to put work on that asynchronous API. If the system is loaded, then the asynchronous call will actually block until it'll block for some time, at most 1 second, and then it'll return, and then the work will proceed after being performed on the caller's thread. Now we could say, and an actual, probably a good thing to say would be that if this call doesn't complete within 100 milliseconds or a second, then just abort the call, so that the caller's threads can't be blocked arbitrarily long. But we don't have the API for that at the moment.
So you're not necessarily queuing things. You say you got work queues here, but you're not queuing work up to, essentially, I throw it over the wall to the system, and I have a work queue there, a prioritized work queue. So why is my thread being blocked at all?
Maybe we can go back one slide,
okay.
And I can explain it in the context of a picture.
Okay.
So in this case, you see the application at the top. The application makes either a submit or a withdraw call. This is an asynchronous call that returns to the application when the work has been placed on the work queue.
Okay.
This is the first arrow from the application into the manager, and then that add call. When that add call completes, then the application's thread is returned to it.
Okay.
When work backs up, the add call will actually block. And what will happen is, after some time, when the load has died down a bit, then the executor will use the caller's blocked thread to complete the work and then return to the caller.
So if I'm calling in through a REST API, then the REST API handler has a limited number of threads. Isn't that going to get a kind of an odd behavior if it uses all the REST API handler threads?
Yeah. So if you had a REST API that was directly calling the intent APIs, then maybe the suggestion that you had earlier, where you could say try this for a fixed period of time, otherwise abort. If it aborts, then you'd return a 500 error or something to the client.
Yeah, I think even internally you'd want kind of, hey, if my queue's too big, and however you define too big, you have policies about dropping and rejecting low priority requests to get queue room because they're never going to be executed anyway, or you just disallow a new add on the queue that says, look, I'm not going to use your thread, but I'm going to tell you my workload's full, go figure it out. And in any case, with prioritization, you're going to have to deal with what happens if everybody starts throwing high priority jobs at you, like a misbehaving client. You're going to have to deal with that anyway in terms of starting to reject things or drop things.
Right, and so the policy that determines what should happen when the queue is full is pluggable. So you could swap this out and you could experiment with things. The other thing that we could get to in a little bit is once we start to leverage stronger notions of applications, then we could have this notion of prioritization, where a security application or recovery application may have higher priority than, say, I don't know, some traffic engineering application or something.
Right.
Yeah, it's a good point, and I think what we'll see is that the asynchronous API is going to possibly need to be extended to support things like try this for a fixed duration, or actually I want a synchronous call or something.
Is the queue ever persisted in terms of if the ONOS crashes? Is everything gone?
So this queue that we're talking about is the mechanism for distributing the state. So this add into the store This is the process by which these things are serialized and distributed to neighbors.
Okay.
And so if anything on the pending queue, if this node crashes, will be lost. And so one of the other advantages of bounding the queue is that you say that you bound the amount of work that can be lost. And if the queue's only 5 seconds long, assuming you can, sustain 10,000 events per second and it's a 50,000 length queue, then you know that only the past 5 seconds of work could have been lost.
Mm-hmm.
So just to add to that, right? So when you say work is lost, so the way the store, at least the intent store is implemented, is that when you write to it, you basically write to the local instance, meaning you basically write to the local store, which could be a local persistent data store, and then you replicate this work to other nodes so that you are creating backups. If ONOS crashes, in the sense that if you restart the JVM, work will still be there if you write it to disk locally, right? And given that the store is designed as an eventually consistent store, and when the store comes up, it is essentially going to replicate the data elsewhere and basically restore the system to like the synchronized state.
Brad,
So,
I have a question.
Sure.
So one of the lessons we learned so far from the Internet 2 deployment is sometimes you have to touch timers you don't expect in the system because the network doesn't behave the way you expect it. And my question is, in what we have now, is how much timer dependencies you have and how it is to make some of those timers easy to for the user to configure them without any, and have some coherent behavior.
So we've actually eliminated almost all of the timers from the system that depend on external events. And so what effectively happens here is the application makes a request. That request is written locally and then distributed to its neighbors. The instance that's responsible for doing the work will pick up the request. We actually have some opportunities for aggregation here. So if you get multiple requests for the same policy, you can actually just throw away all the policies that were older than the newest. Then we write to the store and to the data plane. And so the intents will go into an installing phase, much like the flows go into a pending add phase. And they can sit there for as long as it takes for the data plane to respond. When the data plane responds, then we get the update from the flow service, and we write the state change into the distributed store. And that's the point at which the applications would get the asynchronous notification that their intent has been installed. So there isn't a timer anymore that says, wait for 5 seconds, and if it doesn't happen within 5 seconds, do something. We use events to drive the state machine now rather than waiting on things.
Okay, and there's one question on the line from Murad. You can read it, or I can read it.
Well, yeah, there's a couple of questions. We can go through those. So the first is from David. Any work or thoughts on ONF standardization around intent? I think the answer to that question is for Blackbird. We haven't focused too much on it. We did attend the, Open Daylight, ONF, intent-based networking summit, and we had some good conversations there, I think. We'll look to re-engage with that group in March or April. But I think we do want to be part of that effort going forward. Just we haven't focused too much on that in Blackbird. The next question is, if there is an out-of-memory problem, garbage collection may affect performance also. Yes, and one of the things that we were seeing was that as you get close to as your working set of memory gets close to the JVM limits, garbage collection takes longer and longer, and that can cause work to back up even further. And so, yes, we would like to do longer tests. The tests that we've currently done in the intent framework have been like 1 or 2 hours, but not 24-hour based. And then I guess that's it from the chat questions, unless David wants to ask more.
No, I'm good. I'll be quiet now.
I have a question.
Brian, should that feedback be a back pressure? Because feedback is just, the application may not take an action, but when you back pressure it, potentially you can enforce it.
Well, there's two things here that are at play. The first thing is that we protect ourselves by not letting the system's queues grow unbounded. And the second thing is that if you try to submit work when we're under heavy load, we make the caller's thread pay a penalty by having to wait for a small period of time until the load is able to decrease a little bit. And so, I mean, a caller could, or an application could spin up more and more threads to try to combat this problem. But a normal application is only going to be making these API calls on a small fixed number of threads. And if they're trying to do so at a rate that exceeds the framework's capacity, then all of their threads will be blocked, and that's the back pressure that I was talking about.
Thanks. I have one more question. So initially, the intent framework used the strong consistency for the intent for is due to the fact that we eventually in the future will do some sort of conflict resolution. Now that the intent is eventually consistent, do you have any thoughts on doing the conflict resolution?
Right. So regarding conflict resolution, it's a good question. Actually, the reason that we decided to make the intents fully replicated rather than partitioned for the moment is because we wanted to make sure that all instances had copies of the policy. And the good news, I guess, is that in the new API design, policies are named. So policies that applications know will conflict with themselves. Like if it has to change the behavior of an intent or change add a host, change a route, that intent will be routed to the same instance and treated serially. So we do still serialize intents based on key. But the question is around larger conflict resolution, and I guess we have to talk about it still. We do have access to all of the policies. It's no longer strongly consistent, but there are some thoughts, just roughly, that we may not need to do conflict resolution if we properly describe how intents will interact with each other. But I'm sort of hesitant to make that claim at this point. We did realize, though, that the strongly consistent data structures have a significant impact on performance with really a gain that we were unable to realize at the moment. So that's why we moved to the eventually consistent stores.
That makes a lot of sense to me. I still think that it should be possible to at least detect an intent, both a conflict both at the intent layer and also at sort of the flow rule layer. Once you try to install either an intent or a flow rule that conflicts with one that you already have.
Yeah, it makes a lot of sense, and we need to be able to do it. The one thing that the one other data point that I have in mind right now is the pyretic or frenetic data point. And one of the key features, I guess, of the language is that the way the language is designed, you can't have conflicts. They require that all of your operations be composed in a way that either parallelly or sequentially that defines, like that has well-defined semantics. And so there's not a notion of conflict in a pyretic program. And if we could move to that model in the intent framework where there's well-defined semantics for how an intent between applications or within an application should be combined that are possibly related, it's possible that we could sort of avoid this whole problem of having to detect conflicts at the intent layer. But I guess that's sort of an area that we need to do a lot more research in before we could say that that's our confident that's confidently are going to be our plan.
Let's get back to the performance.
Sure.
Yeah. Okay, Madan.
So there's one more slide on the application framework. Yeah. And the reason that we'll bring this up, it's not strictly performance related, but it is a big abstraction that we've added to the northbound for the Blackboard release. And the idea with the application framework or subsystem is that it's basically a more robust way, a more detailed way of tracking applications and deploying them across the cluster. So we've implemented the application framework with a distributed store. There are CLI and REST APIs for interacting with applications. That's registering these applications with the system. Then they're automatically distributed to all nodes in the cluster. They can be started, they can be stopped, and they can be withdrawn or uninstalled. And this is going to be the basis for security work going into Cardinal. And this is sort of a summary of the presentation that we've seen before. We have 3 plans around the security model. One is bundle level role access control, application level access control, and API level access control. The first 2 of which we can do basically at deployment time with OSGI, and the third of which is going to require a more robust permission system within the application subsystem. So what's actually pretty cool about this is we've used this for our performance testing apps and some other test apps, and it makes it really easy to deploy new applications to the system across the cluster without having to copy jars to individual nodes or try to get them started together. So that's pretty much. Sure. Go ahead, Bob.
To clarify, 1 and 2 are saying that an ONOS application, say a non-administrative application, will be prevented by OSGI from like loading a class file that calls the administrative API.
That's correct.
But at the same
so you can
time,
think of the first one as like the first one we restrict access to the OSGI, or I guess the OSGI bundles based on what which bundles we think that this application should be able to load. The second one is within a bundle we can restrict which services this component can depend on. And then the third one is given a component, we want to be able to restrict which of the APIs or what types of calls can be made to certain APIs. And I can point you to, actually in the comments of this slide on Google Drive, there's a link to the full presentation that describes this security model.
Okay, thank you. Mada?
So yeah, I wanted to sort of give an update on some of the work that we have done, in the Blackbird release. I mean, not just the current sprint, but things that we have accomplished in our sort of, to meet our goal of better performance and stability for ONOS. So one thing that we did is, as Brian alluded to earlier, so the gossip intent store is something that we built. Again, sort of we realized that the use case of storing intents probably would not require a strongly consistent data store, and also that was sort of hurting the performance in some sense. And also just looking at the properties of the data, it felt like having an eventually consistent mechanism would sort of suffice for this use case. So one thing that we did earlier in the release is sort of generalize some of the work that we did in the first release, the work that we did for managing topology state, for example, which we built as an eventually consistent store. In that case, we actually built specific stores which were sort of one-off, doing either device store management or link store management and so on, and sort of extracted these constructs. One of these is an eventually consistent map, which is more general purpose, and it can be sort of used in any application or any other service. And that is what we use in the gossip intent store. So it's basically like a map interface, provides support for full replication, and it also has a pluggable sort of backend storage model, even though right now we only support in-memory maps.
And it also does like some of the things that you need to do for any eventually consistent data structure, which is, how do you sort of how do you detect and resolve conflicts as they occur in the system? So all those things like anti-entropy and replication and everything like comes ready for people to use. So all you need to do is basically initialize this map, and now you have like something which does replication and provides high availability and so on. So that's one thing that that is now available and in use. The other abstraction is basically a strongly consistent map. So there are use cases which sort of like where having an eventually consistent system would probably not work, because they need stronger guarantees. I mean, examples include when you are sort of handing out resources to different applications, you cannot afford to be like loose with like what resources were given out to which applications. So there needs to be a sort of a more a good record of like who is owning what, so that you keep track of what you have remaining, and also like things like leader election and like figuring out who should be responsible for a given task. These are some of the use cases that would benefit from something like this. And some of the known issues with building these strongly consistent systems is that they actually scale very poorly. Like once you go beyond a certain size, like the coordination overhead dominates, and you start seeing poor performance. So one thing that we wanted to do in the Blackbird release is essentially see if we can build a more scalable, strongly consistent data store. And to that end, what we have right now is something that actually does a partitioned, which takes a partitioned approach to this problem. So what we do is basically run multiple. So basically, if you have like a map abstraction, the key space is divided into different partitions, and each partition is essentially, think of it as like a small consensus ring that sort of manages state that maps to that partition. So as you increase the number of nodes, you could sort of add more partitions, and that is a nicer way to scale the amount of work that can happen in the system. So that is something that is right now available, and it is like fairly easy to use. So all you need to do is there is a consistent map interface that is available, and you basically use that if you want to build on top of this feature.
So are we using that version for anything right now, or that's not being used?
So we are right now using it for leader election. So there is a new implementation for leadership service which builds on top of this map.
And then we use multiple rings, or it is a single?
Yeah. So by default, you like if you have a n node cluster, it basically starts up n partitions, n 3-node partitions. So each partition has 3 nodes in it. So that is the default configuration that we have. So if you start up like a cell with 3 nodes, you'll have 3 partitions.
So are there leader election scenarios where you have large number, the key space is that big, or there's a very small key space?
So leader election is not a good sort of use case to demonstrate the scale benefit of this, right? The idea is that there are other use cases where you would want to leverage that. Leader election is sort of something that is built on top of it, not necessarily something that requires like larger scale or like a partition data store.
So we are not really right now not stressing this particular thing.
Right. I mean, we are essentially stressing the correctness of it, but not necessarily the sort of the performance under scale.
Question. So now that you have both the mesh and strong persistent map, so obviously you have to pay penalty costs for the strong persistent.
Yep.
But now that you have both implementation, maybe using similar or same building blocks,
yep,
you can compare them like apple to apple.
Correct.
What is the penalty you have to pay for the strong consistency?
So we haven't done, I would say, like sort of comparison of like. So here's what you should expect, right? So there are like obviously differences in behavior and guarantees that you get with a strongly consistent store that you won't get with an eventually consistent store. An example being conditional updates, right? If you want to say that, only update this if this condition is met, you will not be able to do that in an eventually consistent store. So from a functionality standpoint, there are key differences. If you're okay with either functionality, if you are in the sense that you're using a strongly consistent map as like an eventually consistent stuff, then I would say, again, we haven't done detailed performance measurements, but the key differences right now are anything that you put in the eventually consistent map, at least from a caller perspective, is actually a very low cost operation in the sense that you write locally, right, and then you asynchronously back up to all the replicas, right? So for a user of the map, right, it's actually a fairly quick operation, right? You're essentially reading a local data structure, right? But on a strongly consistent map, when you do a read or a write operation, you actually have to contact a quorum of the partition to get a response.
Okay, so I was thinking more in the context of end-to-end, let's say A says to B, like the ping pong, for example, if you use the eventual consistent versus strong consistent, just like a communication mechanism, then what is the penalty of doing the strong consistency? Even though you may not use this particular deck just to give end-to-end understanding of what is the cost in terms of throughput or
I don't know if I followed that.
So think of it that A and B are using this map for communication. In one case, A writes something, which B receives it in some way.
Correct.
B responds.
Right.
So you could measure the end-to-end latency and throughput.
Right.
And even though A can write very fast, it still gets to wait until it gets propagated back.
Oh, I see. You're essentially using this as a backplane for message passing,
yes.
right?
So if you use it for something like this, then how much penalty you have to pay for the transfer system?
So again, I think we can talk about it. The difference would be that each write and read in a strongly consistent store will have to contact a quorum or contact a majority, at least a majority, right? Whereas in a eventually consistent store, right, you basically have to wait for the message to show up at your local node, right? Typically, that is very fast, right? In a system like ONOS, where it is like running in a clustered environment, you're talking about like sort of 10 gigabit links, so and also very low like sort of error rates. So typically, like the cost that you pay in using an eventually consistent map, assuming you're okay with the semantics that it offers, is actually very low, right? So I don't know if that answers your question, but I don't have exact numbers to.
Well, conceptually, yes. My question was about rough numbers, which probably not that hard to get.
Yeah.
They'll just give understanding at high level what is the actual cost.
Because we don't have the numbers.
Right?
Yeah.
So we haven't done like for a use case like that. It might be good to sort of do these numbers.
Because this will give you some baseline saying.
Yep.
If you want to do something with strong consistency, you cannot go beyond that, just because this is what you.
Right. Again, it depends on like if you want strong consistency, and if you want performance, I think this is sort of the best solution, right? On the other hand, if you don't need strong consistency, then I think you should be okay with using something which is eventually consistent, because you actually get the performance improvement there. So sort of like again continuing with the set of things that we introduced in this release. So leader election is something that we had before. So there was a version of it which we implemented on top of Hazelcast, and it works well until you have a partition in the cluster and you have like to sort of like have a split brain scenario. Hazelcast actually lets you like let someone be the leader for the same topic, like essentially have a situation where the same topic is owned by two different guys on either side of the partition, right? So in that sense, it doesn't really offer strong consistency guarantee unless you are wishing to, pay a penalty by including the entire cluster as your quorum, right? Now we have a implementation which is built on top of, the consistent map implementation, which, again provides you a leader election primitive. That is something that we use in the intent framework as well when we do the execution of intents. There we will let a given node be the owner for a subset of intents. So any intent that sort of maps into that particular intent space gets worked on by that particular instance. So another improvement in this particular release, again, in the previous release we had a implementation based on Hazelcast, was the ability to sort of like maintain cluster membership and detect failures when those things happen. So the one that we added in this release is based on a algorithm or a paper called Phi approval failure detector. So basically what this does is, traditionally failure detectors tell you whether a node is up or down, right? And different applications have different tolerance levels for false positives. So if you prematurely sort of mark a given node as dead, and that results you to take a bunch of actions, sometimes those actions can be very costly. So you want to be, extra sure that this thing is really down, right? So what this failure detector gives you is essentially like a sort of a graduated scale of probability that a given node is down. And applications that need stronger guarantees or stronger assurances that what you're saying is really true, could choose to sort of like set the probability high and only sort of do some like sort of failover actions when they're really sure that the node is down. So this is again something that we have been using as we are doing the intent performance measurements. So there we have seen that under very high load, when you're running high on memory, like things would arbitrarily marked as like down, even though they are like what they are doing is doing a lot of work and therefore like probably not responding to pings in time. What this failure detector also does is essentially adapt to the current network conditions. So the sort of if your pings are slow because the network is congested, or the system is in general under high load, it sort of adapts to that situation as well. So that you don't prematurely mark someone as down. And finally, this is something that we use in the intent framework or the intent execution. So what we do there is, so we want an ability to distribute work amongst ONOS instances, right? Previously we had an abstraction called like basically a distributed queue abstraction. So basically work gets put into that queue and nodes would coordinate to pull work off of that queue. There is some overhead in doing that because you need to sort of ensure that work doesn't get handed over to like the same work doesn't get handed over to two different instances. So the approach that we took here is essentially you take the sort of the logical space into which your work maps to, and then divide that logical space into different partitions, right? Let's say you divide that into fixed number of partitions, and a priori assign ownership of these partitions to ONOS nodes. So essentially, like a given ONOS node will be owning like say 4 out of 14 partitions, right? And you sort of make an effort to evenly distribute the number of partitions amongst the available ONOS nodes. And whenever like this works very well in the context of a fully replicated, eventually consistent map. So whenever you basically get a notification saying that there is a new item in the map, and you basically locally determine whether you are responsible for acting on that update or not, right? And if you are, then you basically get to work on it. And you can be assured that no other instance is actually working on that at the same time. So it sort of gives you that mutual exclusion, but you don't have to pay the cost of like sort of going to some queue to get that work and then sort of coordinate in the process, right? So you initially pay the cost of like dividing up these partitions, and then once you do that, it's just a matter of like basically a local decision to determine whether you should work on a given item or not. Right now, this is not like abstracted or like this is not reusable in that sense. It is sort of a specific solution that we are using in the intent execution system. But the idea is that hopefully we will make this more general and sort of make it reusable in other instances wherever it is applicable. So those are sort of some of the main things that were added in the core subsystem. If anyone has any questions, you can ask them now.
Do you need to ask global lock implementation of this? Or the leader election is taking
this is built on top of the leader election primitive.
So global lock is, you can do it or it is built
So you mean global lock for the?
So if in your application you want some global lock for some reason,
Yeah.
do you have visibility for
Correct.
changeability?
You basically build on top of leader election. Yeah. So you basically define a topic, and that like you can basically run for leadership for the topic, and you are guaranteed mutual exclusion. If a given instance is the owner for the topic, others basically wait until like this node gives up or it dies.
Like in the last point, like the point is to have lock-free execution. But how do you guarantee that? Isn't it going to have a lot of overhead and like how can you converse to the fact that there won't be overlapping or problem of lock and what is the guarantee for that?
Yeah.
How do you guarantee that? Just based on doing a lot of work that it will have a lot of overhead that.
Yeah, I mean that's the idea. Hopefully, I mean the idea is to sort of eliminate overhead when you are getting new work. So the idea is that whenever like a new work item is added, or like I think this works very well in the context of the intent store. Like say when you add a new intent to the system, right? So right now we replicate that intent, like fully replicate that intent. So essentially every instance will have a copy of the, and locally you get a notification when a new intent is added to the system, right? And the idea is that that intent maps to a work queue, right? This logical work queue, and then a given work queue is owned by one partition at any given point of time. So basically they have a lock on it, right? And then you whether this intent maps to a partition that you are the owner for, and if you are, you basically get to work on it.
But it could be based on a lot of replication and a lot of repetition.
So as I said, this works very well in the context of the like fully replicated, eventually consistent store. Yeah. So I think the overhead you're talking about is yes, the replication overhead. Yeah.
Okay. Thank you. Let's move forward with results.
So this spring we did a lot of testing, and together with developers and discussions, we run the bare metal cluster becomes the bottleneck of the resource. So we just built a AWS cluster, so the developer in the next couple of weeks can run works in parallel with the bare metal servers. So during the spring, we also a couple of people alluded to the stability issue that we also run into examples like what is the JVM size we should run the test, the size of flow, the flow rule we're trying to install. They all play into some role of a stability of our testing, and we ended up with running most of the tests under a 1 gig NIC because we've seen some 10 gig NICs, some spurious exception that after a few runs of tests. So we ended up with 1 gig NIC, and we're using 8 gig heap size for the JVM. And the few issues that I listed there is also logged on the Jira. So let's dig into, before we dig into the data, what we're going to do next step is that we're going to run some more testing because the sample size in the current sprint is only run the last couple of days. And then we're going to continue to do more optimization on, what's memory size, NIC cost using 10 gig, and the continuous improvement on the code, and see how we can see the improvement on the performance data. So one thing that we want to see is that also the node provider, at the moment, it has some erratic behavior. Sometimes the link doesn't come up correctly. So we want to explore a little bit more onto the node link providers, make sure that it's stable, because that's essential for intent testing, because the intent has to rely on the underlying topology to being stable. Then it's more about data analysis and abstract the vast amount of data we have to something that's useful for presentation or showcase the capability. So let's go into the results. I wouldn't call this a performance results, more about a baseline. We have a baseline, and data, some of the data we discussed with developer more extensively. Some not, and some are just in the last couple hours come up. So why don't we go from bottom up? If you look at the southbound switch event and port event is something that we have seen in the past couple, maybe past 1 or 2 sprints. So it's nothing surprising. We've seen about 10, 20 milliseconds of latency, and we still need to understand why the latency is so long. One of the areas we're looking for is that the batching of.
What are we?
I don't want to draw too long on this, but this is a switch latency measurement. So we connect an OVS switch to ONOS, and we measure when the graph is seeing the event, and then we scale the cluster from 1 node to 3 node to 5 node to 7 nodes, and see what the latest node will be seeing this event. And what we're plotting on is the latency is the last node that's seeing every node seeing the graph event show up from the switch being connected. So as you can see that we don't have any too much ill effect of scaling out the more cluster having longer latencies. That's one conclusion that I can draw. Although the latency absolute value itself is rather long, it's about 20 milliseconds.
That is the thing, right? Because your absolute latency is so high that extra overhead
that is
annoying.
Right. That's something that we need to look into more next in the next few days.
You know, in these measurements, because I believe there's some mechanism to kind of to sort out some of them.
No, but by theory, we set up the max event equal to -1. It will be not fetching any events. Each link event come up will send up to the graph event. By theory, but we have to confirm.
So this is with real switches.
This is mininet switches.
But still, you go over the network to conduct it.
Yes, but we measuring from TCP SYNAC to the graph timestamp.
You also go to the call exchange mechanism, not only the.
Well, right, all the open flow exchange, but we have broken down most of the latency turned out to be from link. The event show up, the switch event show up on the ONOS to the graph event. So it's not the handshake part of it taking most of the time. All right, can we click the next up? Next one up is a port event. Similarly, we just measure the port up event coming when the open flow message saying that the port status is up to when the graph is seeing the event. So similarly, it's about, there's not much difference among the nodes, but it's about 15 to 20 milliseconds.
It really sounds like you get this additional delay.
So we need to understand what the delay comes from, whether we can reduce that further.
You understand you don't?
We don't at the moment. We haven't spent the time on it yet. Just the last 2. What? We haven't discussed much or investigated much into why the latency is so long. Next one now. So this is an interesting graph that this measurement is measuring network event throughput. If you scroll up a little bit, I think there's a procedure that we're trying to do is that we use this link, no link provider that's flickering to generate link events. And what we're doing is that on ONOS 1, the first node will generate a link event, and then we scale the cluster from 1 node to 3 node to 5 node to 7 nodes, and look at the sustained throughput on the cluster. So what I'm seeing is that with just 1 node standalone ONOS, we can handle more than what the bar showing is not the maximum, because basically I can generate more loading and ONOS still can sustain that load. And so
I'm really not following what the experiment setup is. So what is the experiment setup?
We have a load generator generating link events on ONOS 1. A load generator generating link events on the southbound.
Okay.
Okay. And then what we're trying to measure is that whether ONOS graph event can catch up that load generator rate. If it can catch up, we're saying that that's a sustainable rate for a long period of time, right? So when ONOS cannot sustain that rate, what we're seeing is that the graph rate is dropping lower than the link rate and lower than the generator rate. That's when we determine that's the point that ONOS cannot sustain the rate anymore. And that's what we plot in the data. The throughput is the sustained rate that ONOS can.
So what is it, 10,000?
With the standard ONOS, we can generate more than 10,000. We can sustain more than 10,000 events a second. And that's maximum I generated, but it can sustain. What I'm trying to say is that the note there, the caveat is that on a standalone node, we can sustain very high event rates. And my suspicion is probably can go over 15,000, no problem. Yes. However, when you start clustering it, make it 3 nodes, or 5 nodes, or 7 node cluster, you can see the rate start dropping. At 3 nodes, we can sustain only about 6,000 events per second, and 5 nodes about 4, and 7 nodes about 4,000 as well.
Where are the events generated?
Yeah.
On ONOS 1. Only on 1 node. So the communication will go across the graph.
Right, so you can see some drop, but I think the drop is pretty significant. So some drop makes sense because, again, the same reason that. But
Right. So based on this, we need to do some more profiling and understand why.
Well, I mean, one thing I can think of is, you have more nodes in the cluster, and you're like, let's say, broadcasting to a larger and larger.
Yes,
set.
exactly.
Right, so there is overhead there, so I won't expect this to stay flat.
no, I agree.
Yeah.
So I expect it to drop, right?
Yeah.
And also because you're generating it only on 1 node, if you start generating it on multiple nodes, because when you have a large network, the events will come from multiple nodes, but still the drop seems more significant.
The 5 to 7 is very little, but the significant is from the 1 to 3. So the 5 to 7 is very little.
Well, if you compare 1 to 3, again, 1 is not a limit of ONOS. If you want to really shoot up that rate, they can go really high, right? So that ratio is arbitrary right now. But yes, the significant drop from 1 node to 3 node, you need to understand some more.
Is it tied to your number of cores that you have on your server?
The server is 20 real cores and 40 virtual cores. I mean, hypothetical cores.
Oh, so this is on
Bare metal.
Sorry?
Bare metal.
This bare metal, right? So this is not Amazon.
All right, so let's move up. Next one. Before we go intent throughput, that's going to generate some firestorm. Let's go up. Next one. Intent latency. That's when we install different size of batches on ONOS 1, and then scale out the cluster and look at each cluster when that event, when the intent installation is completed, when we have increasing size of the cluster. And the different bars are showing different intent batch sizes. So 1 intent, 10 intent, 100 intent, 1,000 intent in a batch. Yes.
If the API is asynchronous, how do you know it was installed?
The mechanism of intent push intent will return a intent install success time. Brian, I don't know if you're online. If you're online, maybe you can explain more. That's the test utility that you guys provided. So the push test intent is a utility that push the intent when it's successful returns.
So in this particular case also there must be something like whether you're doing it on 1 instance or multiple instances, and so that is what is.
The installation is always on 1 instance, right? ONOS 1.
Right, but so it is latency, okay.
Right, this is a pure latency, looking at different number, the batch size of intent being pushed into ONOS, and look at the response time.
And this is of the order of what?
20?
And so what are these different things?
Well, each graph shows different intent batch sizes, right? So there are 4 intent batch sizes: 1, 10, 100, and 1,000.
Okay.
Okay. On each graph, we're showing the install time and restore time.
And what are each graph?
And each bar is 1 node cluster, 3 node cluster, 5 node cluster, and 7 node. So we increase the size of the cluster, and we look at the latest response time.
Okay, and the intent requires multiple instances? I mean, does it make use of multiple?
Yes, the intent go across, actually there's an explanation on the top, it's go across end-to-end of the 7 linear switches. That 7 linear switches is master shipped by spreading out.
So there is also some notion of the number of neighbors that we were talking about before?
Definitely, because when you push the intended intent...
So how many neighbors do these intents have?
All of them.
the size.
Every intent has 7 neighbors or 6
The
neighbors?
size of the cluster, right? The size of the cluster vary from one.
The worst case, okay.
Right. So what we're basically seeing that increasing the size of the cluster or sideway communication for the latency didn't seem to be affecting too much by any adverse effect. Whether the absolute number is good or bad, we need to look into it more.
So that is.
This is with the switches.
This is the OBS switches because we couldn't get on the bare metal enough time to run this. This is OBS switches, yes. Come on.
But here from the result we see that the more when you increase the cluster, the throughput will drop and the latency will increase. So basically, when we use the cluster, there should be a gain. So what's the gain by using the cluster?
No, but of this experiment, I don't think you expect to see a gain because you're only installing from one instance. When you look at latency, you install one instance. When everything's on a single local node, that should be the fastest in terms of latency. When you have neighbors, your intent needs to be compiled and maybe flow rule need to be sent out to the neighbors. That obviously is going to.
Have you measured throughput of intent? Oh,
yes. We have some throughput data.
Does that increase the number of instances or number of?
So I think that is what we were talking about, right? I think we did not want to, I think we were not prepared to present those numbers today. Okay. But this is what we were discussing yesterday. Like the throughput is roughly like few thousand intents per second per node. Okay. So this is.
Okay. Is your measurement including the flow rule?
We were using the flow rules.
Okay. Well, we have some data, but I'm not sure it's very preliminary. Maybe it's not explainable, but we're seeing significant performance drop when you start having larger clusters.
Is it drop? But I think you are saying you get 5,000 or whatever, few thousand per, and if you have more thing, then it is. So I don't know what your data is, but then this is not making consistent.
I think we should probably.
Right, we should probably do some more measurement because we didn't have time to.
There has been a lot of changes in what we could do.
Right.
Intents last year. Last week. Starting of last week, we were like, we were barely hitting like few hundred. After like a minute. But now we could like even after an hour we can sustain the same rate that we started. So I think we should definitely sync up and see where these numbers are.
Okay.
And what that means.
Yep.
Okay.
All right. So those are the sort of a baseline data we have so far, and in the next week or two, hopefully we can make some changes and see improvement from there.
And
that's it.
That's all for performance.
Okay.
Okay, so this was the last thing.
Let me check the
Thanks. So of course, in the meantime, if there's any question online,
Luca can answer them.
of course.
Okay, let's should be good.
Okay, so thanks everyone. See you soon.